So our first lesson in this unit was on exponentials. Now we're going to talk about kind of their cousins, and that's the logarithms. One thing we'll talk about a little more as we move on is that logarithms and exponentials are inverses of each other. They do opposite things. Exponentials, you can plug in a very small number and the result will be a very big number. Logarithms, if you plug in a very large number, it will give you a very small number. So they do opposite things, just kind of like x squared and the square root of x. So one place logarithms are used that most people are familiar with is the Richter scale. That's the thing that measures the power or the intensity of an earthquake. So let's look at this example together. It says the magnitude r of an earthquake is r equals log of I over I naught. That little zero is said naught. That's N-O-U-G-H-T if you're curious. So I represents the earthquake's intensity, and I naught is the strength of the smallest measurable earthquake. So I naught doesn't mean zero in the sense that like when there's no earthquake, it means the smallest measurable earthquake. So there is an earthquake, it's just extremely small. The San Francisco earthquake that took place in 1906 was 10 to the 8.3 times more intense than an I naught earthquake. So what was it on the Richter scale? That's what R tells you, is it where it would fall on the Richter scale. So one thing logarithms can do is they can take a very wide range of numbers and try to compress it down for us to help us understand what it would look like, or help us to have it more manageable. Because the Richter scale takes things that can really range from like basically 0 up to 100 billion or even a trillion and condense that down for us, or excuse me, I think, yeah, 100 billion or a trillion, or condense that down for us into a more manageable scale, because the earthquake scale for Richter tends to be between 0 and 10. So 10 to the 8.3, for example, is about 200 million, if I'm remembering correctly. So this earthquake was 200 million times more powerful than the smallest detectable earthquake. So here's how we would approach this. We do R equals log, and for the intensity, what we were told is that it's 10 to the 8.3 times I naught over I naught. So the I naughts will cancel out, and we just have log of 10 to the 8.3. So now we're going to want to plug this into our calculator. We're doing log of 10 to the 8.3. So let's pull up the calculator, and you'll notice there's actually two things that say log. I don't know if I can, I think I can circle them. There we go, yeah. So log log is the one we're using here. That's called the common log, and then ln is the natural log. We'll talk about that a little bit later. So we want to use log, common log. We do log of 10 raised to the 8.3 power. And if we do that, we just get 8.3. So it's 8.3 on the Richter scale. So this was a rather devastating earthquake that happened back in 1906 in San Francisco, and it was 8.3. So the good thing again about logarithms is it kind of compresses an otherwise large range of numbers down for us. But it can also be a little deceiving in some ways, because you hear 8.3 versus say 7.3 and you may be like, okay, well that shouldn't be that different, but they're actually 10 times different from each other. In other words, a 7.3 or excuse me, an 8.3 is 10 times more powerful of an earthquake than a 7.3. So here's another example of how logs might be used. The percentage of an adult height attained by a boy who is x years old can be modeled by the function f of x equals 29 plus 48.8 log of x plus 1. Find the percent height for an 8-year-old. So 8 years old, that means we plug in 8 for x, we get 29 plus 48.8 log of 8 plus 1. So we just plug that in as well. 29 plus 48.8 times the log of 9. 8 plus 1 is just 9. And we get 75.56. So he's about 75.5% of his adult height. Okay, so now let's just talk about them more in general, now that we've seen some places where they're used and can be used. Like I said earlier, exponentials and logarithms are inverses of each other. They do opposite things. And one thing we need to know how to do is convert from exponential form to log form. And the way I remember this is just log BAP. If you look at this, b is our base. If you start over here, b is our base, a is our answer, p is our power. So if you can just remember those things are base, answer, and power, you write log BAP in that order. Base, answer, power. So for an example here, we have 12 squared equals x. Let me space these out a little bit. That'll be a little better. Okay. 12 squared equals x. So I'm wanting to write that as a log. So I do log, and then I put down my base. My base is 12. And then I put my answer, which is x. And then I put my power, which is 2. So these two forms are equivalent. It's just one is exponential form, that's what we started with in black, and we changed to log form, which is what we wrote in blue. So same idea down here. We can do log base b. We have b cubed equals 8, so base b of our answer, which is 8, equals our power, which is 3. So another way to view this is basically that the base stays the same. 12 is the base here, 12 is the base here, and then these two just basically switch places. That's another way you can think about it. Okay, now at the bottom we have e raised to the y equals 9, so we do log BAP. So log base e of 9 equals y, our power. So base answer equals power is how it converts when we do the log. Now one thing to note is just how to read this. Okay, starting with the first one, this is log base 12 of x equals 2. Log base b of 8 equals 3. Log base e of 9 equals y. So make sure that you read it that way. You don't ever say times. It's not log base e times 9. We're not multiplying. It's log base e of 9. Now let's look at how to convert going the other direction. So we have log of 5 equals x. So remember, this is the base, this is the answer, and this is the power. So 5 is the base, x is the answer, 2 is the power. For the next one, b is our base, 64 is the answer, 3 is the power, because it's base, answer, power. Log BAP. Okay, now this one, notice, is written in the other order, but that's okay. It's still log BAP, B-A-P. So base 3, answer 7, power y. So that's how you have to remember to convert them. Now again, these are equivalent. They're just written in different forms. Similar like square root of x and x to the 1/2. Same idea. It's just two different ways to write the same thing. So these are different forms of the same equations. Okay, so we talked about the fact that on your calculator there are two logs. That's the common log, which has a base 10. So if they don't write a base with the log, then it's understood that it's 10. Common log, log base 10. And then the natural log is written ln of x, and that's actually log base e of x. So natural log is just log base e. Remember, e is a number, just like pi. E is 2.71828 or 282 or something like that. So it's 2.71 and so on. In fact, let me just pull that up in the calculator so you can see it. You can use it second divided by, and it pulls up e. You see that number, 2.71828. So there you go. So that's what e is. So the question comes then, well, how do we plug it in our calculator if it's not a common log or a natural log? And that's where this change of base formula comes in. So let's say you have log base b of a. So it's some other base. Then you can just plug in your calculator as log of a over log of b, or natural log of a over natural log of b. You can use either one of those buttons as long as you're consistent. And to me it's simple. B is already written lower on the line, so it goes to the lower part of the fraction. A is already written higher on the line, so it goes to the higher part of the fraction. So in our calculator we can do, to do log base 2 of 16, we can just plug in log of 16 over log of 2. So we can do log 16 divided by log 2. And we get 4. Okay, just for the sake of illustration, let me show you can also do the same thing with natural log. So you can do natural log of 16 over natural log of 2. Sorry about that. There we go. and we also get 4. So it doesn't matter whether you use common log or natural log for this change of base formula. So then the next one you see, log base 3 of 9. We're going to need to do log of 9 over log of 3. So we do log 9 divided by log 3. And we get 2. And again, you could do natural log if you wanted. Okay, now here's some others you could do in your calculator. Log base 4 of 4 to the 5th. So we could do log of 4 to the 5th divided by log of 4. And it turns out to be just 5. So if you look at that for a second, you'll be like, that's interesting. Why did I just end up with 5? Well, if you remember, I told you that logs and exponentials are inverses of each other. So here we have log base 4, and then we have something that's basically of the form 4 to the x, which is exponential. So the 4's cancel each other out, and all it leaves is the 5. So let's look at 6 raised to log base 6 of 9. So let's actually make sure you understand how you'd write this in the calculator. You would do 6 raised to log of 9 over log of 6. So we've got to use the change of base formula. So let's try that. 6 raised to the parentheses. We'll do natural log this time just to show they both work. Natural log of 9 over natural log of 6. And we get 9. So once again, you may notice, hey, all it did was cancel out. This is 6 raised to the something, so it's exponential, and this is log base 6, so they cancel each other out because they're the same base, 6 and 6, and it gives you just 9. Okay, now these last two you can't plug in your calculator because they have x's, but if you follow what I just said about them canceling each other out, it should be pretty simple, because natural log is really just log base e, so that means natural log and e are inverses and should cancel each other out, so it's just going to leave you with 7x. And that's true if you write it the other way. E raised to the natural log of 4x squared. E and natural log will cancel each other out, so it gives you 4x squared.